I think last class we completed output characteristic array. And somebody tell me what was done in the last class. Am I audible? Am I audible?
Yes, sir.
What was done in the last class? I mean, did we complete output characteristic curve last class? I think we did it. I'm not sure whether it was completed or not. Somebody who can say yes or no to it. Kind of. Assuming that we have completed output characteristic curve, which will get into the small signal equivalent model or equivalent circuit. Before we start writing the equivalent circuit, I just wanted to mention something about the output curve, which was discussed in the last class. I assume that we're all done. But just one point to add to it. The graph of VDS versus ID is the output characteristic curve. If I set the value of VG to 0 or VGS to 0, this is a kind of curve what you get. So what do we understand from this? We understand that the resistance offered, there is a resistance being offered, but the resistance offered is less. But as and when you increase the VG value, what you observe is a graph like this. It starts tilting and moving towards the x-axis, and finally it lies on the x-axis. This is what you see. Am I correct?
Yes, sir.
Yeah. So which means that there is a resistance being offered by the channel. That is what is very important for us. If there was no resistance being offered, then with very small VDS value, you could have got a graph like this, a vertical, like this. Okay. We are not getting like this, but we are getting a slope in this fashion, and the slope is very less, and hence the resistance offered is also very less. That is the meaning of it, and it all depends on. It all depends on the VG value. So with this small think about the output characteristic curve, we are good to go write the small signal model. Very first question that we have to answer. When I take a diode, does it possess any kind of capacitance? Do you see any capacitance effect in a diode? What is your answer? Yes or no? Probably most of you will have this question. What is capacitance got to do with the diode? But if at all you have come across or if you have studied anywhere, if you can recall or remember something relating to capacitance and diode, and somebody tell me, is there a capacitance effect in a diode? The answer is yes. The diode possesses the capacitance effect. And the proof is very simple. How do I prove it? You consider a diode, but you're wondering as to why the diode topic is being discussed here, but that has got very much relevance to the junctions what appears in the JFET. This is applicable even to VJTs also. So when you consider a PN junction, what you see here is a depletion region. You all know it. Depletion region is a good insulator because it won't contain any free charge carriers within it. It will not contain any sort of free charge carriers within it. So it's a very good insulator as such. It will allow to pass the electrons and holes through it, but it will not contain within it any mobile charge carriers. If at all the hole has to move, depending on what kind of bias voltage you apply, the whole or electron can move through this. But within that, it will not contain any mobile carriers, and that is why we call it as a depletion region. It is as good as an insulator because any insulator will not contain mobile carriers within it. Okay? And what you see on the either side is a positive as well as a negative. Now, depending on whether you forward bias it or reverse bias the diode, you can see two different capacitance effects coming into picture. Let us forward bias this. When we are forward biasing, what do we mean? We apply positive voltage here and a negative voltage here. We have forward biased it. Now, what happens when you forward bias? The depletion width is going to come down, correct? And all the holes and electrons will start migrating to the other side. Now, if you try to write the equivalent of this, what is happening? You see something like a plate on one side where you have positive, on the other side you've got negative, and in between is what you see a dielectric material. So what we observe is a diode becomes equivalent to a parallel plate capacitor. Parallel plate capacitor. Okay. Where on one side there is a positive, on the other side there is a negative by default because the construction is like that. And in between is a depletion region, which I said it is insulator, and all dielectric materials are good insulators. So this is analogous to a parallel plate capacitor. And what is the equation that we give for a parallel plate capacitor? What equation do we write? C equals I should be getting some response. Otherwise, class becomes difficult. Online classes without response is very difficult.
C1 plus C2.
Okay. What did you say?
So the sum of capacitance.
Sum of capacitance. Where do you see sum of? There is only one capacitance effect here. This is a parallel plate, and what I can write, the distance between these two is some, let us say D. The cross-sectional area of the plate is, let us say, A. The dielectric constant, I can write it as epsilon naught, or epsilon is what I can write. So what is the equation for C I can write? Epsilon A divided by T. This is the standard parallel plate capacitance equation. So what I meant to say is, even for a diode, we can apply this same equation because it is analogous to a parallel plate capacitor. Okay. Now the question here is, if at all you have forward biased it, the depletion width has come down. Correct? The depletion width has come down, which makes the capacitance value to increase. So whatever the capacitance effect you see, let me write that. Whatever capacitance effect we see in the diode, which is forward biased, it is termed as diffusion capacitance. And the name very much matches with the process which is happening. When you forward bias it, there is a diffusion which is really going to happen. Okay, and that is why the capacitance effect is called the diffusion capacitance. It is indicated as CD, capital D. When you reverse bias it, the only change what you see is when you reverse bias it, what happens? Depletion width increases. Remember, the cross-sectional area is all the same. D increases, and hence capacitance effect will reduce. And this kind of capacitance effect is what is called the transition capacitance, which is indicated as CT. So there are two different types of capacitance effect which appears now based on whether you forward bias or reverse bias. So with this basic knowledge on the capacitance effect in a junction or a diode, we are now progressing further into writing the equivalent circuit of a JFET. Okay, first I'll take up the symbolic representation of JFET. We'll see what and all capacitance effect that we can see in the JFET. And this is an N channel. So we are writing it for an N channel. Please remember that. An N channel JFET. Gate, drain, as well as source. We are writing this as this is the layer diagram. P plus. These two are gates. One side is the source, another side is the drain. And we all know, like, how the channel is being controlled. You always give a negative voltage to this. There is always a positive voltage fed to this. So what is the condition of these two junctions now? Getting reverse biased. You see these two junctions also kind of getting reverse biased. And if you try to observe the number of carriers that is placed here compared to that of the drain, there is a concentration gradient because all the electrons will be moving in this direction. So there is a larger concentration available at the drain terminal than the source terminal. So there exists even a capacitance effect between the source as well as the drain. So capacitance effect comes into picture in three different positions. One is between the drain as well as gate, other one is between the source as well as gate, and third one between the drain as well as the source. Let's give the name to all these three. So whatever the capacitance effect that is seen between gate as well as drain, let me call it as CGD. Whatever the capacitance effect that I observe between gate as well as drain, let me call it as CGS. And whatever the capacitance effect that you see between, what is it? Drain as well as source, we call it as CDS. So these are the three different types of capacitors. Now we'll start writing it. And what configuration do we normally assume when we do the analysis of the JFET? It is common source. By default, it is common source. So what should I do? We shall now write the gate terminal at the input side, drain terminal at the output side, and the source terminal right here. So what are we doing? We are trying to use these three capacitors and represent a JFET as a two-port network. So whenever you try to write any device as a two-port network by using components like resistors, capacitors, supplies and all, we say it is equivalent circuit. This was told when we discussed about the diode. Till here all okay? All of you are able to follow till this point? Can I get a consent?
Yes, sir.
Just raise your
Yes,
hand.
sir.
Yes, sir.
And please raise your hand and give a consent. Please, 17, 18, okay. So at least there are 17 to 18 students who are hearing to the lecture. Fine. So now we shall try to write the capacitances. Between the gate as well as the drain, there exists a capacitance called CGD. So let me write the capacitance between gate as well as drain. This is one capacitance. Let me write the line here. Remember, this is a common source. It's very much clear now that this is in fact a common source. Source is made common to both input as well as output. And there is a capacitance effect between the gate as well as source, which we call it as CGS. Please mute your microphone. Somebody has unmuted the microphone. Please mute it. And there's a capacitance between drain as well as the source. CDS. CDS. So this is only a partial equivalent circuit what we have done. Remember in the beginning of this discussion, I told that when we look at the output characteristic curve, we see that there is a resistance effect in the channel. So we can have the resistance effect as far as the gate and drain is concerned, as far as the gate and source is concerned, as well as the drain and source is concerned. So the channel effect, the channel resistance also exists. There exists a resistance between the gate and drain because it is reverse biased. There also exists a resistance between gate as well as source. Even that is also reverse biased because you have more negative voltage being applied to the source than to the gate. Even though both are negative, there is a larger negative voltage being applied to the source terminal. Just try to recall this. I'll write it for your reference. This is how we have written. Even though I'm writing the symbolic representation, but you can just understand. So this is VGS, and what you write here is a VDS source, and this is grounded anyways. This is VDS. So when you vary this, you will vary in steps of, you will vary up till 20, 30 volts. We have seen that in the laboratory also. So this is a larger value compared to VGS. VGS normally goes up till 5 volts, 6 volts like that. In the laboratory, it was around 2.3 to 4 volts where you got the pinch off. Probably around 3.5 you got the pinch off. So this negative voltage, what you apply to the gate is lesser compared to the source negative voltage. So even there also you can see a kind of reverse bias coming into the picture. Okay. So there is reverse biasing everywhere. So there is a resistance. Let me write that now. So we are done with the capacitance effect. We should now worry about the resistances. So there is a resistance effect between gate as well as drain, which I can call it as R, what is it? RGD. There is a resistance effect between what? The gate as well as source, which I can call it as RGS. That's a resistance effect between drain as well as source, which I can call it as RDS. So we've got 3 resistances. Now I should put all the 3 resistors here. So what shall I do? I put the CGS to the other side. So I can call this as CGS. Let me put the resistance between gate and source, or the resistance between gate and source is RGS. You should put a resistance between drain as well as gate, which is RGD, and the resistance between drain as well as source, which is RDS. So this is somehow becoming an equivalent circuit, but still not complete. Any questions at this point in time? Probably I think you should have one question at least to ask. Anybody has got a question? All of you understood how I added and why did I add the resistors and capacitors here? Please one yes or no?
Yes, sir.
So whosoever said yes, and can you tell me why did I add them in parallel? Why did I connect them in parallel? Why can't I connect them in series? Why should I add these 2 resistors? Sorry, a combination of resistors and capacitors in parallel only. I could have done it in series, right? Everywhere I've done it in parallel. So there must be a point behind this as to why did I add them in parallel. Adding these components is very clear, I believe. Why are we adding it? Because they possess, all the junctions would possess these capacitors and resistance effect. But why did I add them in parallel? Any answer? Any good answer for this? I'll give an answer to as to why. I'll go back to the title of this article. What is the title of the article? Title of the article is Small Signal Equivalent Circuit. And remember, our assumption here is, it's not an assumption, the equivalent circuit what we are writing will consider these factors. This input signal, the input signal. When I say input signal, what do you understand? It is the signal which needs to be amplified, and that is what we call it as the input signal. The DC voltages, whatever we represent in input-output characteristics, they're all DC voltages. Remember, okay? They are not the actual input which has to get amplified. So when I say input signal here, it is the signal which needs to be amplified, and that signal is very small. That is one consideration that we take here. And the input frequency is the larger one. So we are considering these two things when I'm writing this small signal equivalent circuit. There are cases where they call the same equivalent circuit as large frequency model, large frequency equivalent circuit. Even this is also correct because the frequency is large, but the signal what you're creating is very small. To give you a clear picture as to what is the meaning of it, I'll take the same circuit what we wrote earlier. I'm writing the amplifier circuit for you. Let us say I'm feeding around 20 volts here. The source is grounded. We are taking the output here. And then the capacitance, which we call the coupling capacitor. And let me connect the resistance here. It's around 1 mega ohm, let us say. And there is a coupling capacitor on the input side, CC1. And I'm feeding the actual input signal which needs to be amplified. VN, let us say. Now this input what you're feeding, which has to get amplified by this amplifier, the signal voltage is very small. I can say voltage is around 10 millivolts peak to peak. But when you are feeding the frequency, you don't go with the smaller values, say around 0 hertz or 10 kilohertz like this. These are all small frequencies. Any frequency, let us say, which is more than 100K, any frequency which is more than 100K is considered to be a large frequency value. So when you are writing this equivalent circuit, you are considering this large frequency. Now most of you will have this question: what is the difference between a small frequency and a large frequency? Voltage is anyway smaller, but the frequencies are different. Is the model going to differ for a small frequency and large frequency? Yes, the model will vary depending on what input frequency you are feeding. I'll give you an example or make you understand as to what is the difference between these two. I'm putting all these statements so that you understand as to why we are writing the two components in parallel. Remember, that is the basic idea behind all these discussions as to why we have to write two things in parallel. So yeah, I hope you are following all these. Are you guys following this? Now, at least you understood this much as to what is the consideration that we're doing, large frequency and small frequency. Say something else. ಅರ್ಥ ಆಗಿಲ್ಲ ಅಂದ್ರೆ ಹೇಳಿ ಅರ್ಥ ಆಗಿಲ್ಲ ಅಂತ ಇನ್ನೊಂದು ಸ್ವಲ್ಪ ಬೇರೆ ತರದ ಹೇಳ್ಕೊಡ್ತೀನಿ. But you should express. Did you follow till this point? These are few things which you may really not be able to understand in one shot. But I'm trying to make you understand all these things because it is required, kind of. We can assume this and proceed further. Write two components in parallel, we can assume it and write it. But I'm just trying to convince you people as to why we are writing it in parallel. And you should get to know this. What is large frequency model? Because this is a very important concept. Nowhere they mention that we are writing this equivalent circuit for a large frequency, even though in a sentence it may appear. But nowhere they say it is a large frequency equivalent circuit. So you should get to know as to why this is called as a large frequency model. I'll give you a simple concept, simple understanding. You take a capacitor. We all know that a junction which is reverse bias will possess capacitance effect. And what is the equation? C equals epsilon A by D. And remember, C value is a very small value when you reverse bias a junction, because D value is a larger value, because the transition region is larger, so distance is also more. So capacitance CT is a very small value. Now let us try to write what is the reactance offered by this capacitor. 1 divided by 2 pi FC. Remember, the CT or CE is a smaller value. What is XC then? For a given frequency, let us not worry too much about the frequency now. For a given CT value, if F is set, what will be XC value? Is it a larger value or smaller value?
Larger value.
XC will be a larger value. Now, worry about the frequency value. If the frequency becomes very small, if F is equal to 0, let us say, now we are considering the smaller frequencies. Let us say, for example, F is equal to 0. What is XC then? XC becomes infinity, correct? XC is going to become infinity. So which means that any smaller frequencies you feed to a transistor at JFET, whatever the junction capacitances that exist in a JFET will become insignificant. Why is that so? Impedance offered by those capacitances, those junction capacitances will become infinity. If the impedance is becoming infinity, it is as good as open circuit. Agree?
Yes, sir.
Agree? Yes. On the other hand,
Yes,
if you
sir.
consider a large frequency, F is, let us say, around 100 kilo, or let us say 1 giga. What is that? I'll consider 1 giga. What will happen to XC? XC will not go to infinity because the frequency is larger. XC becomes a significant value because you cannot open circuit it now. XC is going to become a significant value. It is no more open circuited. You will have to indicate the right value of XC, which means that there is a certain impedance which is minimal being offered by these junction capacitances and you cannot remove it. And remember, at the same time, you've got even the resistors also coming into picture. Resistance is different, capacitance effect is different. You cannot club them together. Getting my point? So now two components will appear, but one of the component becomes obsolete or it will not show its effect when the frequency is very small. But when the frequency is very large, it will show its effect. It will become a significant value which you have to take into consideration. So the reason behind writing two components in parallel, even though this may not be the correct way of giving you the interpretation as to why two components are placed in parallel, but you can somehow understand as to why we are writing it in parallel. If I want to convert this, now I think to this extent, all of you agree that this is a large frequency model. Agree? Why is that so? Because all the junction capacitances have been shown here. We are indicating all the junction capacitances here. And junction capacitances becomes a reasonable value or nominal value at larger frequencies. If I want to convert this into a small frequency model, what will you do? Very simple. At larger frequencies, capacitance are significant. At smaller frequencies, capacitance become insignificant because frequency is low value. So XC becomes infinity. And you'll have to open circuit all those capacitors. So what will happen in the equivalent circuit? You will show only the resistors. Because resistance are independent of frequency component. So this becomes the equivalent circuit at small frequency. At small frequency, this is how you will write the equivalent circuit. Now it becomes very obvious that if I try to indicate these two in series, capacitance as well as resistance in series, when you try to switch to either the large frequency or small frequency, you are going to make a mistake. Supposingly, if you connect two components, RGS and CGS in series, and if you want to convert that into a small signal frequency model, what will happen? Capacitance become open circuited, RGS will be opened there. RGS will no more be connected. So the entire equivalent model will not be correct. And for that simple reason, it will not be the correct interpretation for you as of now. You will study all these things in detail when you go to microelectronics or the basic VLSI part. When you start studying CMOS technology and all those things. But for now, it is really a good convincing answer to say that why two components are placed in parallel. Okay. So this is how we write it. I hope till here things are all okay. I also think that most of you could not understand what was told, but still, is that fine?
Yes, sir.
Good. Okay. So we shall proceed further. So what have I written? Let me erase all the things which are not required here. I did not write what is this. What is this? CGD. It's a CGD. Fine. Are we done with this, or is there anything else also left out here? Have we missed out the most important component? Anybody thinks that we have missed out an important component here in the equivalent circuit? Look at only this equivalent circuit. You're almost coming to the end of the equivalent circuit. Have we missed out any important component here? What you see here is VGS. VGS. And what is this VGS doing? Any change in VGS will change what? Any change in VGS will change what in the JFET?
ID.
Exactly. Any change in VGS is going to change the current which flows in the channel. And the current flows between what and what? The current flows between the drain as well as the source terminal. So I should indicate a current component here which is dependent on VGS value. So it means that I should indicate a dependent current source which depends on the voltage value. And normally, how do you represent a dependent current source? Network analysis, you would have come like this. This is how you indicate a dependent current source. And what is this? This is ID for us. And ID is nothing but, remember, ID is a function of VGS. Any change in VGS is reflected in ID. So let me write it as some K times of VGS. Now, what is this K? Don't tell me it's a constant, even though it can be considered to be a constant. Then what is this actual meaning of K here? K is I equals K times of VGS. K equals I by V. What is I by V? It is conductance. But if you try to see, ID is the output current and VGS is input voltage. So you are relating output and input. And normally when you see the relation between output and input, what is the word that you will use? Relation between output and input. We have done this earlier. Instead of plotting input curve, we plotted something. We called it as
Transfer curve.
transfer curve. So this conductance, what you see, is the conductance which exists between the input-output parameters. So it is called the transconductance. And the notation that we use for this is GM. GM is the notation that we use. So I can represent this current source which gets placed between drain and source as GM times of VGS. So one last thing that I have to add is a current source which exists between, this is RDS, a current source which exists between the drain as well as source. This is what is ID current. Remember, I'm using small subscript here, ID. Do not get confused. Capital ID and small ID will remain one and the same for us, at least in this subject. In this particular subject for third semester, you should not see any difference between a capital ID and small ID. Take it for granted. Okay. If I interchange the subscripts, do not worry. You can write even capital ID or small ID. Only for now, only for this semester. Further, it is going to change. Okay. So I write this as ID, which is GM times of VGS. So this is in a way giving me a complete 95% of the equivalent model. And remember, this is a large frequency model. Small signal, large frequency model. Any questions till this point before I proceed further? If you are referring to the textbook, you know which textbook you have to refer to this? You will not get this in Ben's treatment. You have to refer to, for module 4. Module 4, you should refer to Neiman and Diswas. Write it properly. Neiman and Diswas. The textbook title is Semiconductor Physics and Devices. Only for this, semiconductor physics and devices. This is a textbook what you have to get ready. And if you are referring to the textbook, he uses a different JFET, at least while writing the equivalent circuit. And we have not discussed that in the class. That kind of JFET which is being used here to write the equivalent model is not being discussed because it is not there in the syllabus. And that is the fate of VTU, because they put articles which are nowhere relevant to the previous articles that we have in the module. And they followed it right from module 1. They just misplaced lot many articles which are very important. Anyways, we have to abide by this curriculum sector then and follow it. So what I'm writing here is what is called a MESFET. We know what is JFET, we know MOSFET. There is something called as a MESFET. And this is what is being used in writing the equivalent circuit. It's very, I pretty video as well as the students when we discuss something, we have no relevance and we discuss about it. So anyway, we have to do it. So I'll just give you a brief explanation on this MESFET. MESFET stands for metal semiconductor. Metal semiconductor field effect transistor. It is not metal oxide semiconductor, it is only metal semiconductor. ME stands for metal, that's all. Okay. And the construction of that is this. This is only to, they go for this MESFET only to improvise the switching operation. Switching operation becomes more in this case. Okay. And there are other advantages also, which I do not want to get into. So what they do is they start with a substrate which is made up of plus, and then they diffuse what is called N on the either side. The entire thing will become N now. Let me not write it here. And we require this. This MESFET concept is required here so that we can complete the equivalent model. We have completed 95%, 5% more will be completed using this. And what you see further is a diffusion of P plus, which becomes the gate. Remember, we are talking about an N-channel JFET here. And we place a metal contact to the external world. This is gate. And what you observe is two more contacts on either side. One will be called the source, other one will be called the drain. This is the source, and this is the drain. A small change in the construction, that's all. Earlier, we used to have a, if it was N channel, we used to have the entire substrate or the base to be N type, and on the either side, we were diffusing P. Now, what you see is this kind of thing. Okay. And if you can see the gate here and the substrate are made up of same type, P plus and P plus. Okay. So now I can think of indicating the resistance between the source as well as the gate here. And remember, it is only up till this point. It is only up till this point. The resistance offered here, which is RS. Remember, it's a very small value because the actual current flow will happen only within this channel. So this is what we call it as an active channel region. This region is what is called active channel region. Channel region. This region. Let me show it with an arrow. Sorry. This is the active channel region. Okay. So whatever happens beyond this active channel region is the minimal effect what you observe. So the resistance is what you see here at this region. Let me use a different thing. If you write this and use a different thing. So what you observe here. So what you observe here and here is minimal effect. The resistances at those regions are minimal because there is no active channel coming into the picture. So the active channel comes only within this because the gate voltage gets applied in this fashion. So the active channel region is only this. Remember, the operation will remain the same. Slight difference in the operation. I do not want to get into it. Whatever JFET operation you have understood, in the same way even this also works. Instead of calling the other side as the gate, we are calling it as substrate. Substrate is connected to the supply again. So the same concept remains, holds good even here. But the gate voltage is getting applied only to this region. So that is why we call it as active channel region. So on the either sides, you see minimal effect. So the resistance is also minimal. So what you observe is resistance Rs and Rd between source as well as the active channel region and drain as well as active channel region. So I should indicate a resistance here between the source and the active channel region. So instead of calling this a source now, instead of calling this as, all of you understood what was told? Okay, yes or no to it? Even
Yes, sir.
raising your hand is also fine with me. You just have to get the confirmation that at least we are able to follow 30-40%. Numbers have come down, but at least there are few students who are clearing. Please understand all these, very important. So what shall I do now? I shall now try to represent the resistances chart, source resistance as well as the drain resistance. So I should indicate a resistance between this point as well as the actual source, like this. This becomes the actual source. So whatever you observe is only within the active channel region. So this becomes Rs. And there is a resistance even here also, which becomes RD, a small change that is going to happen. And we also see one more capacitance effect, which is because of the substrate, which is written like this. I do not want to go really in detail about all these things, otherwise we will lose out our actual track. But these three things which are indicated in orange ink are the components which have come into picture because of this kind of MOSFET transistor. Because of this kind of construction of JFET, those three components have come into picture. So what you observe is a capacitance effect between the drain as well as the substrate as well. This is CS. That is because of this fellow as well as the drain film. And that is CS. Okay, substrate capacitance. And that is what is included here. Okay, it comes between the drain and not the source, but the ground point. But the ground point. That source becomes the ground point because source is common here. So that is what is CS. So please understand whatever we had earlier, everything is retained as it is, except that two components of resistance and one component of capacitance is coming into picture because of the MOSFET thing, because of that new type of construction. It is also called the planar construction. It is called the planar FET. So, and the resistance values are very small. You can always eliminate it. This capacitance again is a very large value. You can open circuit it. All those things could be done. Okay. So I'll write the complete equivalent circuit now. How it actually looks. The complete equivalent circuit is going to look like this. Complete equivalent circuit of N channel JFET. RGB CGB, same thing, but just rewriting it. Resistance RGS, capacitance CGS, there is a current source, which you write it as GM times VGS. Remember, this will not be the source. The below terminal is not the source, we can call it as a S dash, which is the intermediate point relating to the source. The actual source comes only after this resistance RS. And this is the source terminal. And what you see here is the resistance RDS, and finally the capacitance, which is CDS, and lastly the substrate capacitance, which is CS. This is the drain. This becomes the complete equivalent circuit of a JFET. You will have to explain this. As we understood the explanation as to why individual components are added here, you also should explain a very probable question, which for sure you will get. All these are connected. All these are connected. So all good till here. Assuming that it's all good till here, we shall now write what is the low frequency small signal equivalent model. Okay, now we shall progress or proceed further into what is called the low frequency small signal equivalent model. So the second half, which is very easy to write. Low frequency small signal equivalent model. Remember, the earlier one was large frequency small signal equivalent model. Now it is low frequency. For your kind information, let me write large frequency small signal complete equivalent model of circuit. Sorry, in channel JFET. Now we are writing the low frequency part. So what in all should I do? What in all should I be doing now? What in all should I do now? I'll have to remove all the capacitors and replace it by open circuit. Remove all capacitors and replace it by a open circuit. The resistors, what are indicated there, are large resistance values because VGS is coming into picture now. For VGS equal to 0, if you remember the output characteristic curve, for VGS equal to 0, the resistance offered was very less. As and when you increase the VGS value, the resistance increases. So all resistors, one second, all resistances again open circuited because we assume it to be a larger value. So all the resistors are open, all the capacitors are open. If you want, you can retain these all resistors open circuited. You can consider it to be a large value, but still acceptable, and you can retain it. But these are the two considerations that we will do in writing the small signal model. Remember, the resistors can be retained. It shall be retained if you want, but we'll write the approximate model here. This is what is approximate model. We are doing approximation here. So whatever approximations we can do, we'll do it to the fullest possible extent. So what happens? What is going to happen between the source as well as drain? Sorry, gate as well as source. Both these are removed, becomes open circuit. Both these are removed, become open circuit. Both these are removed, become open circuit. You can short circuit this RD because it's a very small value. You can as well short circuit this RS, even that is also a very small value, as I told earlier. And the only thing which is left out is GM times the VGS between gate as well as the source terminal. So the entire equivalent model what we have written gets reduced to this gate. Do you see anything between gate as well as source? Do we have to write anything between gate as well as source? Say something. None of you understood what was told. Just speak out something. This is the problem with online classes. No response, even I cannot do anything. I have to hit my head, that's all. I cannot scold you. I cannot point out any student. What exists between at the output between drain as well as source is only this component. Gm times of VDS. This becomes the equivalent circuit which is at low frequency and small signal. And when low frequencies are there, as I already told, capacitor should get open circuited. We also do not consider the resistances also. Even those resistances are high when you are giving a larger VGS value. With this, the concept of equivalent circuit is all done. Next is to get to know the frequency limitation factor and what is called as a cutoff frequency, which we shall understand it in the next coming class. Third hour, I've got again a class. Your DSD sir has assigned the class to me. I'll be taking the class. This class is also scheduled. We've got 10 more minutes. I think we'll start with that article. What do you say? Will we proceed with that article? ಕೇಳಿಸ್ತಾ ಇಲ್ವೇನಪ್ಪ ಮಾತಾಡ್ತಿರೋದು?
Yes, sir.
ಅರ್ಥ ಆಗ್ತಿದೆಯಾ ಹೇಳ್ತಿರೋದು ಎಲ್ರಿಗೂ?
Yes, sir.
ಹಾ, ಸ್ವಲ್ಪ ಹೇಳ್ಬೇಕು.
Yes,
ಎಸ್ ಅನ್ನೋ ಅಂತ ಹೇಳ್ಬೇಕು. ಯಾಕಂದ್ರೆ ಇದು ಆನ್ಲೈನ್ ಕ್ಲಾಸಸ್ ತುಂಬಾ ಕಷ್ಟ ಆಗತ್ರಿ. Conducting online classes is very, very difficult for a faculty because we look at the faces and then we deliver the lecture. I'm looking at the screen now. It's a very pathetic moment for a faculty. ನೀವು ಆರಾಮಾಗಿ ಕೂತ್ಕೊಂಡ್ಬಿಟ್ಟಿರ್ತೀರಾ, ಹಾಸಿಗೆ ಮೇಲೆ ಮಲ್ಕೊಂಡಿರ್ತೀರಾ, ಇಲ್ಲ ಇನ್ನೇನೋ ಮಾಡ್ತಿರ್ತೀರಾ. ಫ್ಯಾಕಲ್ಟೀಸ್ ಹಂಗೆ ಮಾಡ್ಲಿಕ್ಕೆ ಆಗೋದಿಲ್ಲ. You should respond to the question. At least say something. ಅರ್ಥ ಆಗ್ಲಿಲ್ಲ ಅಂತ ಹೇಳೋದು ಬೇಜಾರು.
ಆಫ್ಲೈನ್ ಕ್ಲಾಸಸ್ ಯಾವಾಗಿಂದ ಸರ್?
ಗುಡ್ ಕ್ವಶನ್ ಕಣ, ನಂಗೆ ಐಡಿಯಾ ಇಲ್ಲ ಕಣ.
ಸರ್ ಅದು ಬೇರೆ ಕಾಲೇಜ್ಗೆಲ್ಲ ಆಫ್ಲೈನ್ ಇದೆ.
ಬೇರೆ ಕಾಲೇಜ್ಗೆಲ್ಲ ಆಫ್ಲೈನ್ ಕರೀತೀರಾ?
ಹಾ ಸರ್.
ಗೊತ್ತಿಲ್ಲಪ್ಪ ಇನ್ನು ಅದೇನೋ ಅಂಟಿಲ್ ಫರ್ದರ್ ಸರ್ಕ್ಯುಲರ್ ಆರ್ಡರ್ಸ್ ವಿ ಕೆನಾಟ್ ಕಂಡಕ್ಟ್ ಆಫ್ಲೈನ್ ಕ್ಲಾಸಸ್. ಅದು ಕನ್ಫ್ಯೂಷನ್ ಬೇಡ ಅಂತ ಹೇಳಿ ಒಂದು ಮೋಸ್ಟ್ಲಿ ಈ ವಾರ ಮಾಡ್ತಾರೆ ಅಂತ ಕಾಣುತ್ತೆ. ನಾಟ್ ಶ್ಯೂರ್, ಎನಿಥಿಂಗ್ ಕ್ಯಾನ್ ಚೇಂಜ್ ಅಟ್ ಎನಿ ಪಾಯಿಂಟ್.
ಎಂಟ್ರೆನ್ಸ್ ಆನ್ಲೈನ್ ಅಥವಾ ಆಫ್ಲೈನ್
ಅದು ಗೊತ್ತಿಲ್ಲ ಕಣ. ಈವನ್ ದಟ್ ಈಸ್ ಆಲ್ಸೋ ನಾಟ್ ನೋನ್ ಟು ಅಸ್. ಎವ್ರಿಥಿಂಗ್ ಆಸ್ ಆಫ್ ನೌ ಇಸ್ ಆಲ್ ವಿಥೆಲ್ಡ್. ಸದ್ಯಕ್ಕೆ ಎಲ್ಲದನ್ನು ಸ್ಥಗಿತವಾಗಿದೆ, ಏನು ಹೇಳಲಿಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ಲ. ಅದು ಪ್ರಿನ್ಸಿಪಲ್ ಜೊತೆ ಡಿಸ್ಕಸ್ ಆದ್ಮೇಲೆ ಫೈನಲೈಸ್ ಆಗುತ್ತೆ. ಈಗ ವಿಟಿಯು ಪ್ರಕಾರವಾಗಿ ಆಫ್ಲೈನ್ ಆಗಿರೋದ್ರಿಂದ ಟೆಸ್ಟ್ಗಳು ಆಫ್ಲೈನ್ ಆಗಬಹುದು. ಬಟ್ ಡಿಪೆಂಡ್ಸ್, ಈ ವಾರ ನೋಡಿ ಮೋಸ್ಟ್ಲಿ ಡಿಸಿಷನ್ ತಗೋತಾರೆ ಅಂತ ಕಾಣುತ್ತೆ. ಆಕ್ಚುಲ್ ಆಗಿ ಆನ್ಲೈನ್ ಟೆಸ್ಟ್ ಮಾಡೋದು ಅಂತ ಆಗೋಗಿತ್ತು, ಬಟ್ ಈಗ ವಿಟಿಯುನೇ ಹೇಳಿರೋದ್ರಿಂದ ಆನ್ಲೈನ್ ಟೆಸ್ಟ್ ಕಂಡಕ್ಟ್ ಮಾಡೋದು ಕಷ್ಟ, ಮೋಸ್ಟ್ಲಿ ಡೌಟ್ಫುಲ್. ನೋಡೋಣ, ವಿಲ್ ಸಿ. ಫಾರ್ ದ ಟೈಮ್ ಬೀಯಿಂಗ್ ಇಟ್ಸ್ ಆಲ್ ವೆರಿ ಅನ್ಕ್ಲಿಯರ್ ಫಾರ್ ಅಸ್. ಯಾವುದು ಕ್ಲಾರಿಟಿ ಇಲ್ಲ. ನಮಗೆ ನಿನ್ನೆ ರಾತ್ರಿವರೆಗೂ ಕ್ಲಾರಿಟಿ ಇರಲಿಲ್ಲ, ಆನ್ಲೈನ್ ತಗೋಬೇಕು ಆಫ್ಲೈನ್ ತಗೋಬೇಕು ಅಂತ. ಐ ಆಮ್ ನಾಟ್ ಫೀಲಿಂಗ್ ವೆಲ್, ರಿಯಲಿ ನಾಟ್ ಫೀಲಿಂಗ್ ವೆಲ್. ಸೊ ನಾನು ರಜಾ ಹಾಕೊಂಡಿದ್ದೆ, ಇವತ್ತು ರಜಾ ಹಾಕಿದ್ದೀನಿ. ಇನ್ಫ್ಯಾಕ್ಟ್ ಮನೆಯಿಂದ ಕ್ಲಾಸ್ ತಗೋತಾ ಇದ್ದೀನಿ. ಸೊ ಅದಕ್ಕೆ ಆಫ್ಲೈನ್ ಆನ್ಲೈನ್ ಡೌಟ್ ಇತ್ತು. ಸೊ yesterday night it got clarified that there will be online classes today until further orders. ಫರ್ದರ್ ಆರ್ಡರ್ಸ್ ಯಾವಾಗ ಬೇಕಿದ್ರು ಬರ್ಬೋದು. ಇವತ್ತೇ ಬರ್ಬೋದು, ಇಲ್ಲ ಈಗಲೇ ಬರ್ಬೋದು, ಇಲ್ಲ ಇನ್ನೊಂದು ವಾರ ಬಿಟ್ಟು ಬರ್ಬೋದು. ಎನಿಥಿಂಗ್ ಕ್ಯಾನ್ ಹ್ಯಾಪನ್. So till then we'll have to wait. So not clear about it.
ಓಕೆ ಸರ್, ಥ್ಯಾಂಕ್ ಯು.
ಸೊ ಅರ್ಥ ಆಗ್ತಿದೆ ಅಂತ ಅನ್ಕೋತೀನಿ. ಸ್ವಲ್ಪ ಕೆಲವು ಕಾನ್ಸೆಪ್ಟ್ ಅರ್ಥ ಆಗೋದು ಕಷ್ಟ. Even I understand, I do understand. Few concepts are very difficult to understand. ಅದು ಕ್ಲಾಸಲ್ಲಿ ಹೇಳ್ಬೇಕಾದ್ರೆ ಡಿಫ್ರೆಂಟ್ ಆಗಿರುತ್ತೆ. ಯಾಕಂದ್ರೆ ಕ್ಲಾಸಲ್ಲಿ ಮುಖ ನೋಡಿ ಪಾಠ ಮಾಡ್ತಿರ್ತೀವಿ. ಇಲ್ಲಿ ಒಂದು ಫ್ಲೋ ಅಲ್ಲಿ ಹೋಗ್ತಾ ಇರ್ತೀನಿ. ಮೋಸ್ಟ್ ಆಫ್ ಯು ಮೇ ನಾಟ್ ಬಿ ಏಬಲ್ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್. ಮಧ್ಯದಲ್ಲಿ ನಿಲ್ಲಿಸ್ಬಿಟ್ಟು ಕೇಳಿದ್ರೆ ಸ್ವಲ್ಪ ಡಿಫ್ರೆಂಟ್ ಆಗಿ ಅಥವಾ ಇನ್ನೊಂದು ಸ್ವಲ್ಪ ಕ್ಲಾರಿಟಿ ಬರೋ ತರಕ್ಕೆ ಕಾನ್ಸೆಪ್ಟ್ ನ ಹೇಳ್ಕೊಡ್ಬಹುದು. ಬಟ್ ಹೇಳ್ದಾಗೇನೆ ಕೆಲವು ಆರ್ಟಿಕಲ್ಸ್ ಗಳೆಲ್ಲ ತುಂಬಾ ಅಬ್ರಪ್ಟ್ ಆಗಿ ತಂದ್ಬಿಟ್ಟಿದ್ದಾರೆ ಸಿಲೆಬಸ್ ಅಲ್ಲಿ. ಕೆಲವು ಇರೋದಿಲ್ಲ, ಬಟ್ ಆದ್ರೂ ನಾವು ಮಾಡ್ಬೇಕಾಗತ್ತೆ. ಸೊ ಆ ಥರದ್ದೆಲ್ಲ ಇದೆ ಇದರಲ್ಲಿ. ದಟ್ ಪ್ರಾಬ್ಲಮ್ ಇಸ್ ದೇರ್. So then I openly express in front of students so that they also understand the difficulty in it. ಮಾಡಬೇಕಾದ್ರೆ ತುಂಬಾ ಲೆಂತಿ ಆಗುತ್ತೆ, ಮಾಡದೆ ಹೋದ್ರೆ ಅರ್ಥ ಆಗೋದಿಲ್ಲ. ಸೊ ಆತರ ಇಟ್ಸ್ ವೆರಿ ಸಿಚುವೇಶನ್ ಇಸ್ ಅ ವೆರಿ ಡೈಲೆಮಾ. ಸೊ that is why. Anyways, 9:25 will be leave the class. ಇವಾಗ ಕ್ಲಾಸ್
ಸರ್, ಅದು ಸೆಕೆಂಡ್ ಟೆಕ್ಸ್ಟ್ ಬುಕ್ ಇದ್ರೆ ಶೇರ್ ಮಾಡ್ತೀರಾ?
ಇದ್ರದ್ದು ಒಂದು ನಿಮಿಷ ನೋಡ್ತೀನಿ. ನನ್ನ ಹತ್ರ ಇರೋದು ಡೌಟ್ ಅದು. Just check it once. ಟೆಕ್ಸ್ಟ್ ಬುಕ್ ಇಲ್ಲ, ಆಫ್ಲೈನ್ ಆನ್ಲೈನ್ ಸಿಗ್ಲಿಲ್ಲ. ಅದು ಇದೆ. ಇದು ಹಳೇ ಇದಪ್ಪ. ಇದು ಇದೇನಿದೆಯಲ್ಲ, ಇದು ದಿಸ್ ಇಸ್ ಅ ವೆರಿ ಓಲ್ಡ್ ಎಡಿಷನ್. ಇದು but I'll share it, go
Hmm.
through it. Okay, go through it. You can at least somehow manage this part. PPT
Okay,
part
sir.
ಆಗೋದಿಲ್ಲ. ಶೇರ್ ಮಾಡಿದ್ದೀನಿ ನೋಡು ನಾನು ಇದರಲ್ಲಿ.
ಹಾ ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಓಕೆ, ವಾಟ್ಸ್ಆಪ್ ಗ್ರೂಪಲ್ಲಿ ಶೇರ್ ಮಾಡಿದ್ದೀನಿ ಈಗ. 2021 textbook. Shared. You already shared it. You can just go through it. ಒಂದ್ಸತಿ ನೋಡಿ. Okay. So we'll wind up the class for now. Thank you. Thanks a lot. You can leave the class. Attendance I'll take it online. Online ಯಾರಿದ್ದೀರಾ? ಎಲ್ಲದಕ್ಕೂ ಬಂದಿದ್ರೆ